In this lecture, I am going to present what is consistent deformation method and what is propped cantilever beam and how to determine the redundant reaction of the propped cantilever beam by consistent deformation method. Then I would like to solve three problems using consistent deformation method. So first coming to what is consistent deformation method. Consistent deformation method is used to calculate reactions and internal forces in statically indeterminate structures due to loads and imposed deformations. In this method, the redundants are identified first by removing restraint in the direction of redundants. Then the release structure or determinate structure is obtained. Then apply these redundant as load acting on the basic determinate structure. Then in the determinate structure, the displacements are obtained in the direction of the redundant. Then the displacement due to each redundant are obtained and the conditions of displacement compatibility are imposed to get the additional equations. Solution for these equations gives the value of redundants. Then in the determinate structure subjected to these known forces, the moment and shear force can be determined. This method is suitable when the number of unknowns are 1 or 2. Then coming to what is propped cantilever. We know that a cantilever is a beam with one of its ends fixed and the other end free. It is a determinate structure. Therefore, we can easily calculate the bending moment and shear force in a cantilever beam. However, when the free end of the cantilever is supported by a prop, so this type of beam is called the propped cantilever beam. In the case of propped cantilever beam, due to this additional support, a reaction is set up. Already there exists a vertical reaction and movement at the fixed end. Along with these two reactions, one more reaction at the prop end is added. So a propped cantilever will have three unknowns, but under vertical loading we have only two equations of static equilibrium, namely summation of vertical force is equal to 0 and summation of moment is equal to 0. Hence, one of the reactions cannot be determined with the application of these static equilibrium equations. Because of this, a propped cantilever becomes an indeterminate structure. The degree of static indeterminacy is equal to 1. Therefore, we require one more equation to solve the problem. The third equation can be obtained from the consideration of deflection or slopes. That is from the compatibility condition. So this is the propped cantilever. So this propped cantilever, so this is the fixed end, the end A is fixed and the end B is propped end. So this propped cantilever can be solved by using the consistent deformation method to find out the unknown reaction at the propped end. This propped cantilever can be evaluated by two cases. In first case, if the reaction at the propped end is treated as redundant, the resulting basic determinate structure is a cantilever. If we will choose the reaction as a redundant, so the basic structure becomes the cantilever, that is determinate structure. If you treat the fixed end moment as the redundant, the resulting basic determinant structure is a simply supported beam. By using the reaction as a redundant, we can use the cantilever beam, or by taking the moment as a redundant, we have to use the simply supported beam. And by using these two determinant structure, so we can solve the propped cantilever beam. So any of the above two basic determinant structure can be used for the analysis of the propped cantilever beam. Let us consider a propped cantilever AB. The end B of the beam is propped. Let us take a point load or uniform distributed load is acting on the beam. At the end A is fixed. It has vertical reaction RA and moment MA. Besides, there is one more vertical reaction at B, that is RB, at the propped end. If the reaction is treated as redundant, then how to evaluate the reaction at the propped end? So what are the steps we have to follow to find out the reaction at the propped end? First step, we have to remove the prop at B. With the removal of prop, the beam has become a cantilever. Now we can calculate the downward deflection at the free end. First we have to remove the reaction at the propped end, and we have to find out, due to the given loading, what is the downward deflection. Then in second case, so we have to remove the external loading, whatever may be the loading, a point load or UDL, we have to remove the external loading. Then we have to apply the vertical reaction at the propped end, that is in upward direction. Then we have to evaluate what is the upward deflection at the free end. Then we know the net deflection at the propped end is 0. So by using this equation, the redundant can be evaluated. After knowing the redundant reaction at the end B, the moment at A and the reaction at A can be easily evaluated. So this is the process used to analyze the propped cantilever beam by consistent deformation method. Then coming to the first problem, the cantilever beam shown in figure has a rigid support 10 mm below the free end. Analyze the beam for the loading shown, given EI is equal to 150,000 kilonewton meter square. So this is the cantilever beam, and here the end A is fixed and this is the end B. Just below 10 mm having a rigid support at B. The length of the cantilever beam is 6 meter, and there is having two concentrated load at a distance 2 meter from the fixed end A and at a distance 4 meter from the fixed end A. The first load, which is acting at a distance 2 meter from the A, that is 40 kilonewton, and the second load, which is acting at a distance 4 meter from the A, and that is 60 kilonewton. Then how you have to evaluate the prop reaction at the end B. So this is the rigid support, and the rigid support is present just below the 10 mm from the free end B. So here, what is the reaction at the rigid support that you have to evaluate? Let's take the vertical reaction at B, that is RB, and that is treated as a redundant reaction. Then by removing the restraint to this redundant, we get a cantilever as the basic determinant structure. First we can evaluate downward deflection delta due to 40 kilonewton and 60 kilonewton load by removing the redundant. Then evaluate upward deflection delta 1 due to redundant by removing the external load. Then by equating the upward and downward deflection, that is the consistency conditions, delta 1 is equal to delta minus 0.010, will get the redundant. So this is the beam. Here by removing the redundant, and this is the cantilever beam, and here only by using the external load. So you have to find out what is the downward deflection delta. So this is the determinant beam subjected to external loading 40 kilonewton, 60 kilonewton, and you have to find out what is the downward deflection at the free end. So this is the first step. In the second case, you have to remove the load and you have to take the upward reaction at B. That is, you have to take the redundant at B, and due to this redundant, you have to find out what is the upward deflection. So this is determinant beam subjected to redundant force RB, and due to this redundant force, you have to find out what is the upward deflection, and that you have to take delta 1. If there is no support 10 mm below the free end, the deflection of the cantilever delta is equal to deflection due to 40 kilonewton load plus deflection due to 60 kilonewton load. So here you have to find out deflection delta due to 40 kilonewton load and due to 60 kilonewton load. If there is no support at the free end, so by removing the rigid support at the free end, so you have to find out what is the deflection due to this 40 kilonewton load and due to this 60 kilonewton load here. So delta is equal to deflection due to 40 kilonewton load plus deflection due to 60 kilonewton load. So delta is equal to, so here you have to find out, so due to this load, what is the deflection here, then what is the slope here, then you have to find out what is the deflection here. Similarly, due to this load, you have to find out what is the deflection just below the load, and you have to find out what is the slope below the load. Then you have to find out what is the deflection here. Then you have to take the sum of the two deflection here. You know, for concentrated load, so what is the deflection and what is the slope. If the concentrated load is acting at the free end, then what is the deflection at the free end? That is equal to WLQ by 3I. Then what is the slope at the free end? That is WL square by 2EI. So here this is the 40 kilonewton load that you have to take as a concentrated load, and what is the deflection here? So this deflection is equal to 40 into 2Q by 3I, and what is the slope here? 40 into 2 square by 2EI. Then what is the deflection due to 40 kilonewton load? What is the deflection of the free end? So this is equal to 40 into 2Q by 3EI plus 40 into 2 square by 2EI into 4. So this is the distance between this and this. From this to this, so this length is 4 meter and this length is 2 meter. So here, what is the deflection here? Plus, what is the slope here? And what is the distance between the free end and this load? So this is the deflection due to the 40 kilonewton load is equal to 40 into 2Q by 3I plus 40 into 2 square by 2EI into 4. Similarly, so due to this 60 kilonewton load, so you have to find out what is the deflection here and you have to find out what is the slope here. So the deflection here is equal to 60 into 4Q divided by 3EI, and the slope under the 60 kilonewton load, so this is equal to 60 into 4 square by 2EI. Then by considering this slope and deflection below this load, then you can find out what is the deflection at the free end. So due to 60 kilonewton load, so this is the deflection 60 into 4Q by 3EI plus 60 into 4 square by 2EI into 2. So this is the distance between 60 kilonewton load and the free end. This one, this is 2 meter. So this is the total deflection due to the 40 kilonewton load and due to the 60 kilonewton load. Then after simplification, the delta is equal to 2666.67 divided by EI, but we know EI is equal to 150,000 kilonewton meter square. Then you have to put this value here. Then after simplification, delta is equal to 0.01777778 meter, and this is downward deflection. Then in second case, so you have to take the upward reaction and you have to remove the downward load, and due to this upward reaction or due to this redundant, you have to find out what is the upward deflection, delta 1. The upward deflection due to RB is equal to delta 1. So delta 1 is equal to RB into 6Q by 3I. So this is the total length from fixed end to this prop reaction. This length is 6 meter. So RB into 6Q by 3I. So this is equal to the upward deflection. But here EI is equal to 150,000 kilonewton meter square. Then after putting this, delta 1 is equal to RB into 6Q by 3 into 150,000. What we know, what is the consistency conditions? So this is equal to delta 1 is equal to delta minus 0.010. Then after substituting the value of delta and delta 1, then we can evaluate the reaction at B. So the reaction at B is equal to RB, that is equal to 16.20 kilonewton. Then after knowing the reaction at B, then you can find out what is the reaction at A and what is the moment at A. If you know the reaction at B, then you can find out what is the reaction at A and what is the moment at A. So the reaction at A you can find out by taking the summation of vertical force is equal to 0. That is by taking the downward force is equal to upward force, you can find out what is the vertical reaction. Then you can find out the moment here. You have to take the moment of all the forces, that is RB into 6 meter anti-clockwise positive and 40 into 2 meter clockwise negative and 60 into 4 meter clockwise negative. So this is shear force at A is equal to summation of vertical force is equal to 0, upward force is equal to downward force. The vertical reaction at A is equal to 40 plus 60 downward force minus the upward reaction. 16.20 is equal to 83.80 kilonewton. So this is the vertical reaction at A. Then find out the moment at A. MA is equal to RB into 6 meter minus 60 into 4 minus 40 into 2 is equal to minus 222.8 kilonewton meter. The moment at A is the hugging moment. So this is equal to 222.8 kilonewton meter. These are the moment and the reaction at the fixed end A that you can find out after knowing the reaction at B. Then coming to the second problem, the cantilever beam shown in figure of span 4 meter is supported by a 2 meter long 3 mm dia wire CB. Determine the force developed in the wire. Given EI is equal to 5000 kilonewton meter square and the Young's modulus of the wire is 200 kilonewton by mm square. So here this is the cantilever beam is given and the length is 3 meter and 1 meter, 4 meter. The UDL 20 kilonewton by meter is having up to the length 3 meter, that is for the portion AD. And this is the wire. So this wire is fixed at C and this is tied to this cantilever at B. And this length of the wire is given 2 meter and the diameter of the wire is given 3 mm. So you have to find out what is the force developed in the wire. By removing the wire, you have to find out what is the downward deflection. In the absence of wire BC, let the deflection of B in the cantilever AB be delta. So here you know the UDL is present up to the length 3 meter, but you have to find out what is the deflection at the free end B delta. So delta is equal to, you have to find out what is the deflection at D and what is the slope at D. Then you can find out what is the deflection at the free end. So delta is equal to YD plus theta D into 1 meter. So you know, so due to the uniform distributed load, so what is the deflection at D? YD is equal to 20 into 3/4 by 8 EI. And what is the slope at D? Theta D is equal to 20 into 3Q by 6 EI. Slope at D, that is theta D, is equal to 20 into 3Q by 6 EI. Then you can find out what is the deflection at the free end B delta. So delta is equal to 20 into 3 to the power 4 by 8 EI plus 20 into 3 to the power 3 by 6 EI into 1. Then delta is equal to 292.5 by EI. Then after putting the value of EI, then you can find out what is the downward deflection due to the given loading UDL. So delta is equal to 0.0585 meter. So this is the downward deflection due to the loading in the absence of wire BC. Then in second case, you have to find out, this is the wire, let the force developed in the wire be P. Then by considering this, so you have to find out what is the extension of the wire by using the relation delta 1 is equal to PL by A. So you have to find out the downward deflection or the extension of the wire P. This is the unknown force in the wire, so that you have to evaluate, and the length of the wire is given 2 meter. So you have to take in millimeter P into 2000. Then the diameter of the wire is given 3 mm. So here you have to take the area pi by 4 into 3 square. The modulus of the wire is given 200 kilonewton by mm square. Then you have to put here E is equal to 200. So the delta 1 is equal to P into 2000 divided by pi by 4 into 3 square into 200. Then after simplification, delta 1 is equal to 1.41471 P. So this is the extension of wire, but you don't know what is the force in the wire. So the extension of wire delta 1 is equal to 1.41471 P. Then you can convert to the meter. Delta 1 is equal to 0.00141471 P meter. So this is in millimeter. Then you have to convert to meter by dividing 1000. Then it becomes delta 1 is equal to 0.00141471 P meter. Then you have to find out the upward deflection due to this force P, that is equal to delta 2. Delta 1 is equal to the extension of wire and delta 2 is the upward deflection. So delta 2 is equal to P into 4Q divided by 3EI. Then after simplification, delta 2 is equal to 4.26666 into 10 to the power minus 3 meter. We know from the consistency conditions, delta is equal to delta 1 plus delta 2. So this is the downward deflection due to the external loading, and this is delta 1 is the extension due to the wire, and this is the delta 2 is the upward deflection due to the force P. Upward deflection due to the force P. Then delta is equal to delta 1 plus delta 2. Then after putting the value of delta 1 and delta 2, then you can find out what is the force in the wire P. that is 0.0585 is equal to 0.00141471 p plus 4.26666 into 10 to the minus 3. Then after simplification of this equation, then you can find out what is the force in the wire. So the force in the wire is equal to P is equal to 38.335 kilonewton. Then coming to the third problem, the beam AB of span 3 meter rests over another beam BC of span 2 meter as shown in figure. If a 60 kilonewton load acts on beam AB at 2 meter from A, find the reaction at the support A and C given the flexural rigidity of the beam AB is twice that of beam BC. So here you have to find out what is the reaction at A and what is the reaction at C. And this is two beam. This is two beam, and the beam AB is rest over the beam BC. Here the flexural rigidity of AB is twice that of BC. So let us take the flexural rigidity of AB is equal to EI, and the flexural rigidity of BC becomes EI by 2. And the length of the AB is given 3 meter and length of BC is given 2 meter. And one load is having at a distance 2 meter from the fixed end A. And the intensity of load is given 60 kilonewton. By removing the beam BC, so you have to find out what is the downward deflection due to the external loading. So here, if the beam is not resting on BC, it will deflect by BB1. So here, the downward deflection BB1, that you can denote by delta. So this you can find out at the free end, the deflection of the free end you have to find out due to the external loading. You know the load is given 60 kilonewton at a distance 2 meter from the fixed end. So first you have to find out what is the deflection just below the load and what is the slope at that point. So what is the deflection here? The deflection here is equal to 60 into 2q divided by 3ei. And what is the slope here? The slope is equal to 60 into 2 square by 2ei. Then you can find out what is the deflection at the free end. So the deflection at the free end B1 is equal to delta. So is equal to 60 into 2q by 3ei plus 60 into 2 square by 2ei. And what is the distance between them? What is the deflection here? Plus slope into the distance between this load and the free end, 1. Then you can find out what is the deflection of the free end. Delta is equal to B1 is equal to 160 by EI plus 120 by EI is equal to 280 by EI. So this is the downward deflection due to the external loading. Let the reaction at BBP. So this beam is resting over the beam BC. Let the reaction at B is P. This force pushes the beam AB up by B1, B2 to bring it to the final position. So this upward force P that pushes the beam to the upward direction and that brings the beam to this position B1 to B2. B1 to B2. This is delta 2. So B1, B2, that is delta 2 is equal to P into 3Q divided by 3ei. So after simplification, delta 2 is equal to 9P by EI. Then the reactive force P on beam BC will bring down B by delta 1. Then what is the force which is acting on the beam BC? That brings the beam by delta 1 downward direction, B to B2. So the downward force at B on the beam BC that brings the beam to this position, that is B to B2, B to B2, that is the deflection delta 1. So BB2 is equal to delta 1, so is equal to P into 2Q by 3EI BC. So here the length of the beam BC is given 2 meter and the flexural rigidity is given EI by 2. So what is the force acting on the beam BC? That you have to find out the downward deflection. So the downward deflection is equal to delta 1 is equal to BB2, and that is equal to P into 2Q divided by 3EI BC. 3EI BC. P into 2Q by 3EI BC, but you know EI BC is equal to EI by 2. Then after putting, so delta 1 is equal to 8P by 3EI by 2, then this is equal to 5.3333 P by EI. So this is the downward deflection due to what is the reactive force P acting on beam BC, and the deflection is delta 1. Then from the consistency condition of deformation, the total deflection delta is equal to delta 1 plus delta 2. So here you know delta 2, that is this deflection you got due to the upward force here on the beam AB, and delta 1 you got due to the downward force on the beam BC. Then the total deflection delta is equal to delta 1 plus delta 2. Then after putting the value of delta 1 and delta 2, then you get the force P is equal to 19.54 kilonewton. Then after knowing the force P, what is the force is acting on AB and what is the force is acting on BC, then you can find out what is the reaction at A, what is the moment at A, similarly what is the reaction at C and what is the moment at C, because here what is the force you are getting here. So for this AB, so this is acting upward, and for BC this is acting downward. Then you can find out what is the vertical reaction at A. Then you can find out the upward reaction at A by considering the summation of vertical force is equal to 0. And this is the load acting on AB, and this is the force at B, the reaction at B. So VA is equal to downward force minus upward reaction at B. 60 minus 19.54. So this is equal to 40.46 kilonewton. Then you can find out what is the moment at A. Here you know what is the force here you got. So this force into 3 meter minus 60 into 2 meter. This is the moment at A. The force you got here 19.54 kilonewton into 3 minus 60 into 2. This is equal to minus 61.38 kilonewton meter. So this is the moment at A. Similarly, you can find out what is the reaction and moment at C. So here the force is having P 19.54 kilonewton downward. The same reaction you get at C. Vc is equal to 19.54 kilonewton. Then you can find out what is the moment here, because here you know the force P is equal to 19.54 kilonewton, and this is the length 2 meter. So the moment at C is equal to 19.54 into 2. So this is equal to, the MC is equal to 19.54 into 2 is equal to 39.08 kilonewton meter. So this is the moment and the reaction at C. Now all are clear what is consistent deformation method and what is propped cantilever, and how to analyze the propped cantilever by using the consistent deformation method. Then how you have to find out the reaction or forces and the moment at other location of the beam.